All right, let's talk about one of the most powerful ideas ever dreamed up, calculus. Now, I know, the name sounds a little intimidating, but stick with me. Because at its heart, calculus isn't really about crazy complicated equations. It's actually a beautiful story about solving two massive and, for a long time, seemingly impossible problems. So, let's start with the first big problem. Imagine you're driving. Your speedometer says you're going 60 miles an hour. But what does that actually mean, right at this very instant? I mean, think about it. Speed is distance divided by time. But in one single frozen moment, zero time has passed and you've covered zero distance. So how can you even have a speed? This little paradox absolutely stumped the greatest minds for centuries. And then there was this other puzzle. Finding the area of a square or a triangle. Easy. We've been doing that for ages. But what about something with curves? Like the area under a flowing, swooping line on a graph. How in the world could you measure that weird, irregular space with perfect accuracy? These two problems, finding an instantaneous speed and finding the area of a curvy shape, they really felt like two completely separate mountains to climb. Okay, let's tackle that first mountain, the whole instantaneous speed problem. As it turns out, the key isn't about freezing time, it's actually about looking at it a different way, geometrically. It's all about figuring out the steepness of a line, or what mathematicians call the slope. See, if we were to graph a car's journey, its speed at any given moment is just the slope of the graph at that exact point. But look at this thing. A real journey isn't a straight line, is it? It's a curve, and its steepness, its slope, is changing all the time. So how do you find the slope of just one single point on a wobbly line like this? Well, here is the absolutely beautiful, almost shockingly simple solution. If you pick a point on any smooth curve and just zoom in on it closer and closer and closer, something amazing starts to happen. That curve begins to look like a perfectly straight line. And finding the slope of a straight line? Hey, we know how to do that. That's easy. This incredible idea has a name, the derivative. The derivative is the tool that calculus gives us to find the exact slope of that infinitely zoomed-in line. It's the answer to our first question. It gives us that instantaneous speed, that precise rate of change in one perfect moment. Now, the real genius here is that you don't have to do that crazy zoom-in trick every single time. That would take forever, right? What mathematicians discovered were these elegant patterns, these shortcuts. For any function, like x to the power of n, its derivative follows a simple, predictable rule. And it's these patterns that make calculus such an incredibly powerful and fast tool. All right, one problem down, one mountain climbed. Now let's switch gears and go to that second one, figuring out the precise area under a curve. How on earth do we measure a shape that's so awkward? Well, a pretty clever way to start is to use what we can measure easily, good old-fashioned rectangles. We can try to fill up the space under the curve with a few of them. It's not going to be perfect, of course. You can see all the little gaps and the bits that hang over, but it gets us in the ballpark. It's an approximation. But now, here comes the leap of genius. What if we make those rectangles thinner and thinner and thinner still until they are infinitely skinny? What happens then? Well, as you cram an infinite number of those little slivers in there, all those errors, the gaps, the overlaps, they just vanish. They get squeezed out of existence, leaving you with a perfect fit. And this process, this idea of summing up an infinite number of tiny, tiny pieces to get a perfect whole, yep, you guessed it, that has a name too. It's called the integral. It's the tool that gives us that one perfect, exact area. And just like that, problem number 2 is solved. So we did it. We have our two solutions for our two very different problems. But the real revolution, the climax of this whole story, is discovering how these two ideas are connected. I mean, just think about it for a second. We've got derivatives, which are all about finding the slope at a single point by zooming way in. And then we've got integrals, which are about finding a total area by adding up an infinite number of pieces. One's about division and shrinking down. The other is about addition and building up. They feel like they come from totally different universes. Or are they actually two sides of the exact same coin? This is it. This is the big one. The fundamental theorem of calculus. This single equation is the secret bridge that connects everything we've just talked about. It tells us that finding the total area under a curve isn't some impossibly long addition problem. No, it's way simpler. It reveals this deep, hidden relationship between slopes and areas. And honestly, it's one of the most important discoveries in the history of human thought. So what does this all mean? It means that finding a slope, what we call differentiation, and finding an area, what we call integration, are exact opposites. They are inverse operations. They literally undo each other, just like multiplication undoes division, or taking a step forward undoes taking a step backward. And let me tell you, this discovery wasn't just some neat mathematical trick. It fundamentally changed our ability to describe, predict, and build the world around us. Here's why that connection is such a game changer. Because they're opposites, we don't have to go through that infinitely long process of adding up rectangles anymore to find an area. Instead, we can use those simple, fast rules for derivatives and just work backwards. It's the ultimate mathematical shortcut. And this shortcut unlocked, well, basically everything in the modern world. It's the math that lets us model the orbits of planets. It's behind the design of every safe bridge and every fuel-efficient airplane. It helps economists predict market trends. It even helps create the stunningly realistic graphics you see in movies and video games. Anything that changes or moves or grows or accumulates relies on this fundamental connection. So in the end, calculus gave us a language to describe a universe that is constantly in motion. It took two ancient, impossible questions and revealed that they were just mirror images of each other, unlocking the secrets of how things change from one moment to the very next. And that leaves us with the most exciting thought of all. If this is the language of change, what incredible story are we going to tell with it next?